The night sky hides a truth far stranger than fiction. Our most fundamental ideas about space and time are being overturned by cosmic phenomena we are only beginning to grasp. This journey through 25 of these discoveries will fundamentally change how you see our place in the universe. We will uncover why the cosmos is flying apart faster and faster, driven by an invisible force, and what it means that most of the matter in the universe is completely undetectable. What single cosmic mystery makes you question the nature of reality itself? The universe is not simply growing, it is racing outward at a pace that grows faster with every passing moment. This astonishing discovery, which completely overturned our vision of the cosmos, earned its pioneers the Nobel Prize and forced us to rewrite the story of everything. Astronomers made this breakthrough by observing distant stellar explosions, expecting to measure how much the universe's expansion was slowing down. Instead, they found the opposite. The expansion was speeding up, as if some invisible pressure was pushing the very fabric of space apart. We call this mysterious force dark energy. It is the dominant component of our universe, making up about 68% of everything that exists, yet it remains completely invisible to our telescopes and undetectable by any direct means. Physicist Saul Perlmutter, one of the leaders of the teams that made this discovery, reflected that the finding was a complete shock. It meant that the universe's future was entirely different from what we had thought. This mysterious pressure finds a home in Einstein's old idea of the cosmological constant, a kind of built-in energy of empty space itself. While gravity pulls matter together, dark energy acts as a sort of cosmic antigravity, pushing everything apart on the largest imaginable scales. This leads to a profoundly lonely future, often called the Big Freeze, where galaxies will drift ever farther apart until the cosmos becomes a vast, dark, and cold expanse. The evidence for this is now etched into the afterglow of the Big Bang itself, the cosmic microwave background, which confirms the presence and power of this enigmatic force. So what does it mean for our understanding of reality that the fate of the entire cosmos is dictated by something we cannot see, touch, or directly measure? This invisible pressure that governs expansion finds a strange partner in the cosmos, another profound mystery that binds the universe together. While dark energy pushes the cosmos apart, a second, invisible force works in perfect opposition, holding it all together. The galaxies we see spinning in the night sky are cosmic illusions. Their visible stars and gas merely the glittering surface of a much deeper reality. The true architecture of the universe is built from dark matter, a substance that does not emit, absorb, or reflect any light at all. We cannot see it, but we can feel its gravitational hand shaping everything. The first compelling evidence for this cosmic phantom came from the meticulous work of astronomer Vera Rubin. She studied how stars orbit the centers of spiral galaxies, expecting the outer stars to move slower, just as Pluto orbits our Sun more slowly than Earth. Instead, she found stars at the very edges of galaxies whipping around at incredible speeds, speeds that should have flung them out into the void. The only explanation was that each galaxy was embedded within a massive, invisible halo of matter, a gravitational glue holding the entire structure together. We observe this hidden scaffold through another cosmic trick of the light, a phenomenon called gravitational lensing. The immense gravity of dark matter warps the very space around it, bending the light from distant galaxies as it travels toward us. This creates shimmering arcs and multiple images in our telescopes, like a cosmic mirage revealing the silhouette of the unseen. For decades, scientists have been hunting for the particle responsible, building incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the faintest whisper of a dark matter particle interacting with ordinary matter. So much of the cosmos is built from this ghostly material, yet it remains utterly alien to us. If the vast majority of matter in the universe is completely invisible and unknown, how can we possibly claim to understand the true nature of reality? This unseen architecture forces us to look back to the very first moments of everything, where another profound mystery was imprinted on the cosmos. Every cosmic structure we see, every galaxy held in the grip of dark matter, traces its lineage back to a single, unimaginable event. This was not an explosion within the void, but the violent birth of the void itself. The Big Bang marks the moment when space and time began their existence, erupting from a point of infinite density and temperature. A Belgian priest and physicist named Georges Lemaitre first proposed this radical idea, calling it the hypothesis of the primeval atom. He suggested the entire observable universe was once condensed into a single, immensely hot and dense state, and has been expanding ever since. For decades, this remained a compelling theory, until two radio astronomers named Arno Penzias and Robert Wilson made a chance discovery. They detected a faint, persistent hiss coming from every direction in the sky, a uniform microwave signal that was the cooled remnant of the universe's first light. This cosmic microwave background was the smoking gun, the afterglow of the Big Bang's initial fireball, and it confirmed that our universe indeed had a definite beginning. To understand this genesis, we must follow a breathtaking timeline. In the first fleeting fraction of a second, a period known as the Planck epoch, all the fundamental forces of nature were unified into a single superforce. Then, in an event called inflation, the universe underwent an exponential growth spurt, expanding faster than the speed of light and smoothing it to an incredible degree. As the cosmos cooled, the forces we know today, gravity and electromagnetism, the strong and weak nuclear forces, peeled apart from one another. In the first few minutes, a process known as nucleosynthesis forged the lightest elements, hydrogen and helium, from a searing soup of particles. It took hundreds of thousands of years for the universe to cool enough for electrons to combine with nuclei, forming the first stable atoms in a pivotal moment called recombination. This finally allowed light to travel freely, creating the cosmic microwave background we observe today. Picture the universe's expansion not as galaxies flying through space, but as the space between them stretching like dots on the surface of an inflating balloon. Every point recedes from every other point with no true center. How does comprehending a universe with a definite beginning alter our perception of time and existence? It suggests that time itself is a property of our cosmic reality, not an absolute backdrop. And if our universe had a beginning, what kind of ending, or perhaps transformation, awaits it? From this fiery birth, we are drawn to its potential mirror opposite, a place where the rules of reality break down completely. The fiery beginning of the universe inevitably leads us to its potential end. Our cosmic destiny is not written in stone, but is instead a battle between two invisible titans, the relentless outward push of dark energy and the inward pull of gravity. The ultimate fate of everything we know hinges on the outcome, and cosmologists have envisioned three profound endings. The first is the Big Crunch, a dramatic reversal of our current expansion. In this scenario, the collective gravity of all the matter in the universe, both seen and unseen, eventually overpowers the push of dark energy. The cosmos would slow its expansion, halt, and then begin to collapse in on itself. Galaxies would rush together, space would shrink, and the temperature would soar, culminating in a fiery conclusion where everything is pulled back into a state of unimaginable density, a mirror of the Big Bang in reverse. A second, even more violent possibility is the Big Rip. Here, dark energy does not just win, it becomes dominant in a terrifying new way. If this repulsive force were to grow stronger over time, it would eventually overcome every force that holds things together. First, galaxy clusters would be torn apart. Then, individual galaxies, the gravitational bonds holding stars, would snap. Planetary systems would be shredded. In the final moments, the force would rip apart stars and planets, and finally, it would tear apart atoms and the very fabric of spacetime itself. The third, and currently most supported by our measurements, is the Big Freeze or heat death. This is a slow, quiet end. The expansion continues forever, steadily diluting the universe. Stars will eventually burn out one by one until no new ones can form. Galaxies will fade to black, and the universe will approach absolute zero, becoming a vast, dark, and incredibly dilute sea of fundamental particles. Cosmologist Brian Greene noted that contemplating these endings forces us to confront the transience of all structure. The path we are on is determined by a critical density parameter, a single number that describes the balance between the universe's expansion energy and the pull of gravity. Our most precise observations of dark energy suggest this number points toward the Big Freeze, a cold, eternal fade. What does it mean for our endeavors, for the legacy of intelligence, that the cosmic stage itself may be destined for such profound silence? This ultimate destiny is not written by stars or galaxies, but by the strange, empty space between them, a vacuum humming with a hidden energy that dictates our fate. The profound silence awaiting the cosmos is an illusion, for the vacuum of space itself is not empty. It is a vibrant, seething sea of energy, constantly bubbling with activity. This is the bizarre domain of quantum fluctuations, where the very concept of nothingness is rewritten. At the tiniest imaginable scales, governed by the Heisenberg uncertainty principle, particles and their antimatter counterparts spontaneously flicker into existence, borrowing energy from the void for an impossibly brief moment before annihilating each other and vanishing. These are virtual particles, and their transient lives are a fundamental feature of reality. This quantum fizz has a tangible effect we can observe in the laboratory through the Casimir effect. When two incredibly smooth metal plates are placed extremely close together in a vacuum, the gap between them is so narrow that only certain wavelengths of these virtual particles can appear inside. Outside the plates, a wider variety of fluctuations can occur, creating a subtle pressure difference that actually pushes the plates together. It is a detectable force born from the energy of seemingly empty space. This idea extends to the grandest of scales. The theory of cosmic inflation suggests that in the first split second of the universe, microscopic quantum fluctuations were stretched to unimaginable sizes by the rapid expansion. These tiny ripples in the fabric of spacetime became the gravitational seeds for everything that followed, the blueprint for all the galaxies and vast cosmic voids we observe today. If the very void is alive with this transient energy, a constant dance of creation and destruction, does true nothingness even exist? This ephemeral nature of particles, popping in and out of reality, connects directly to one of the most famous and powerful ideas in all of science. The ephemeral dance of virtual particles points to a far deeper truth, a fundamental equivalence written into the very laws of reality. It is a relationship so profound that its simple formula is now recognized across the globe: E equals mc squared. Albert Einstein's theory of special relativity revealed that mass and energy are not separate things at all, but two interchangeable forms of the same underlying essence. The equation states that energy is equal to mass multiplied by the speed of light squared, a number so astronomically vast it defies everyday intuition. This means a single gram of matter, something with negligible weight in your hand, contains within it the energy equivalent of the bombs used in the Second World War. This is not merely a theoretical concept, it is the engine that powers the stars. Deep within the Sun, intense pressure and heat force hydrogen nuclei to fuse into helium. In this process, a tiny fraction of their mass is annihilated, transformed directly into pure energy according to Einstein's rule, providing the light and heat that has sustained life on Earth for billions of years. This principle reaches its ultimate expression in the phenomenon of matter-antimatter annihilation, where a particle meeting its antiparticle results in their total masses being converted into a tremendous burst of energy, a perfect demonstration of mass as concentrated energy. Einstein himself reflected on the power of this idea, suggesting that for the rest of his life he would want to understand what an atom is. The equation forces us to redefine our notion of substance. If a rock, a star, or your own body is ultimately just a highly concentrated, stable form of energy, then what truly separates the tangible solidity of matter from the vibrant, energetic fields of the quantum realm? This blurring of the line between stuff and energy is the key that unlocks our understanding of the cosmos's most violent and creative events. The ultimate expression of mass converting into energy is found where gravity wins its final, absolute victory. Within the heart of a collapsing giant star, a point is reached where the outward pressure from nuclear fusion can no longer withstand the relentless inward crush of its own immense gravity. The core implodes, and if the remaining mass is great enough, it collapses all the way down to an infinitely dense point, a singularity. This creates a black hole, a region of space-time where gravity is so powerful that the escape velocity exceeds the speed of light. Nothing, not even a single photon, can break free from its grip. The boundary of no return is called the event horizon, a one-way membrane shrouding the singularity from our view. The mathematics describing this eerie reality emerged directly from Albert Einstein's theory of general relativity. A German physicist and astronomer named Karl Schwarzschild, while serving on the Russian front during the First World War, found the first exact solution to Einstein's equations that described such an object. For decades, black holes remained a theoretical curiosity until technology finally caught up with theory. In April 2019, the Event Horizon Telescope collaboration, a global network of observatories acting as a single Earth-sized instrument, released the first ever image of a black hole. It was not a picture of the black hole itself, which is invisible, but of its shadow, a dark silhouette encircled by a brilliant, lopsided ring of superheated gas swirling at the precipice. These cosmic phenomena come in different scales. Stellar mass black holes formed from dying stars pepper our galaxy, but at the center of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole containing the mass of millions or even billions of suns compressed into a region no larger than our solar system. Their gravity dictates the motion of entire galaxies, and as matter spirals into their event horizons, it forms an incredibly hot, glowing accretion disk that can outshine all the stars in the galaxy combined. They warp spacetime so severely that they act as natural cosmic lenses, bending the light from objects behind them. Yet their most profound mystery is not what they consume, but what they might destroy. When anything crosses the event horizon, it is lost to our universe forever. This presents a fundamental conflict with quantum mechanics, which insists that information can never be truly destroyed. So what happens to all the information describing a star, a planet, or a book that falls into a black hole? Does it vanish from existence, or is it somehow preserved on the event horizon's surface, a cosmic hologram encoding its final moments? The answer may lie not in their immense gravity, but in the faint, slow leakage of energy that suggests even these cosmic vaults are not entirely sealed. Even the universe's ultimate vaults are not perfectly sealed. Stephen Hawking made a startling theoretical leap, proposing that black holes are not truly black, but can slowly evaporate by emitting a faint glow of radiation. This idea bridges the colossal gravity of general relativity with the fuzzy uncertainty of the quantum world. the mechanism unfolds right at the precipice of the event horizon. The quantum vacuum constantly spawns pairs of virtual particles, one with positive energy and one with negative energy. Normally, these pairs annihilate each other almost instantly. But if this dance occurs right at the black hole's boundary, a bizarre theft can happen. The particle with negative energy can fall across the event horizon, while its partner with positive energy escapes into space. From a distant vantage point, it appears the black hole has just emitted a particle. To balance the cosmic books, the black hole must pay for this emission with its own mass, shrinking by an infinitesimal amount. Hawking realized this process means black holes have a temperature directly related to their surface gravity. Smaller black holes are hotter and evaporate far more quickly than their gigantic, supermassive cousins. Over timescales that dwarf the current age of the universe, an isolated black hole would slowly radiate away its entire mass, culminating in a final, explosive release of energy. As Hawking himself famously said, it shows that black holes ain't as black as they are painted. They are not eternal prisons but dynamic objects with a life cycle. This profound insight creates a deep puzzle known as the black hole information paradox. If a black hole evaporates completely, what happens to all the information about the stars and planets that fell into it? Quantum mechanics insists that information is never lost, only scrambled. Does Hawking radiation somehow encode the history of everything the black hole ever consumed? Or does it truly vanish, forcing us to rewrite the laws of physics? This quantum gravitational riddle is a critical piece of the greatest quest in modern physics, the search for a single, unified theory that can describe all of reality, from the smallest quanta to the grandest cosmic horizons. How does the slow, quiet evaporation of a black hole, a process linking the very large and the very small, challenge our most fundamental ideas about permanence and information in the cosmos? The slow evaporation of a black hole reveals a fundamental crack in our understanding of physics. We are left with two magnificent, yet incompatible, descriptions of reality. On one hand, we have general relativity, which masterfully paints the cosmos on its grandest scales, describing the graceful curvature of spacetime around stars and galaxies. On the other, we have quantum mechanics, which with stunning accuracy governs the chaotic, probabilistic world of atoms and subatomic particles. Each theory is spectacularly successful in its own domain, but they speak different languages and obey different rules. Unifying them into a single, coherent framework, a so-called theory of everything, is the single greatest challenge in modern physics. This is the quest for quantum gravity. The central conflict is stark. General relativity presents a smooth, continuous universe where space-time is a flexible fabric. Quantum mechanics reveals a world that is fundamentally grainy and uncertain at the smallest scales. So what happens where gravity is incredibly strong and distances are vanishingly small, like at the heart of a black hole or the first moment of the Big Bang? Our current laws simply break down, yielding nonsensical answers of infinite density. This forces physicists to ask a breathtaking question. Is spacetime itself, the very stage upon which the universe plays out, actually composed of discrete, indivisible units? Two leading candidates offer radically different answers. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy or strings. Just as different vibrations of a violin string produce different musical notes, the diverse vibrations of these fundamental strings are thought to give rise to all the different particles and forces we observe. To make the mathematics work, string theory requires extra dimensions of space, curled up into sizes far smaller than an atom. In this view, the universe is a kind of cosmic symphony. The competing approach, loop quantum gravity, takes a more direct path. It suggests that spacetime itself has a discrete, atomic structure. Picture the fabric of the cosmos not as a smooth sheet, but as a network of incredibly fine woven loops. Space is not infinitely divisible. It is composed of a finite number of these quantum units, a billion times smaller than an atomic nucleus. Time, too, may advance in these tiny, discrete steps rather than as a continuous flow. The challenge with both of these extraordinary ideas is profound. The energy scales required to probe such tiny structures are far beyond the reach of any particle accelerator we could ever build. How do you test a theory that describes the very foundation of reality itself? Some hope lies in searching for subtle imprints from the early universe, or in studying the Hawking radiation from black holes for a signature of quantum gravity. If we were to discover that space-time is indeed quantized, it would force a revolution in our thinking as profound as the one Copernicus began. The continuous reality we perceive would be an illusion, a seamless tapestry woven from countless individual threads. What would it mean for our concept of movement, of cause and effect, if the universe itself operates in the tiniest of clicks, like the frames of a cosmic film? Our reality may be a mere slice of a far richer cosmic landscape. The 3 dimensions of space and one of time that we experience so directly could be just the beginning, a visible fraction of a universe built with many more hidden dimensions. This is not science fiction, but a serious implication of our most ambitious attempts to unify physics, particularly string theory. For the mathematics of string theory to work, to describe all the forces and particles as vibrations of tiny strings, it requires extra spatial dimensions. Not 1 or 2, but 6 or 7 additional dimensions, curled up and compactified at a scale so incredibly small that they are completely hidden from our everyday perception. Think of a long garden hose viewed from a great distance. It appears to be a simple one-dimensional line. But if you could shrink yourself down to the size of an ant crawling on its surface, you would discover a second dimension, the circular dimension wrapped around the hose's circumference. Our universe might be like that, with these extra dimensions curled up at every point in space, at a scale a billion times smaller than an atom. This radical idea might even solve a long-standing cosmic mystery, the puzzling weakness of gravity. Gravity is vastly weaker than the other fundamental forces. The electromagnetic force that holds molecules together is stronger than gravity by a factor of 1 with 40 zeros behind it. Why is the force that shapes the grand cosmos itself so incredibly feeble? The answer could be that gravity is not weak at all. Instead, its influence may be leaking away, spreading out into these hidden extra dimensions, which dilutes its strength in our familiar 4-dimensional realm. How could we ever detect something so elusive? Scientists are searching for subtle experimental signatures. In powerful particle colliders like the Large Hadron Collider, researchers look for events where energy seems to vanish without a trace. This missing energy could be a telltale sign that a particle, such as a graviton which carries the gravitational force, has momentarily departed our dimensional brain and carried its energy into the wider, higher-dimensional bulk of the universe. Other experiments probe gravity at microscopic distances, searching for any deviation from its familiar inverse square law, which would be a clear signal that gravity is behaving differently as it probes these tiny, compactified spaces. To perceive a higher dimensional reality directly would be beyond our biological capacity, but we can try to conceptualize it. A 3-dimensional being like ourselves can see the entire inside of a 2-dimensional square drawn on a page. In the same way, a 4-dimensional being could look down upon us and see the inside of every room in a building, the contents of every safe, and the inner workings of our own bodies all simultaneously. It is a perspective that defies our intuition, suggesting that the solidity and separation we experience is a profound illusion. If the cosmos is indeed built with these hidden dimensions, what other fundamental truths are simply beyond our current capacity to see? This search for the universe's hidden architecture leads us to question the very shape of the cosmos on its grandest scales. The very fabric of the cosmos may be curved on a scale so vast we can barely perceive it. To understand the universe's ultimate architecture, we must ask a deceptively simple question. What is its overall shape? Cosmologists have narrowed the possibilities down to three profound geometries, each with staggering implications for the fate of everything. The first is a flat universe, an infinite and Euclidean expanse where parallel lines never meet, and the rules of geometry are as we learned in school. The second is a closed universe, a finite but unbounded cosmos that curves back on itself in a higher dimension, much like the surface of a sphere. If you could travel in a perfectly straight line in such a universe, you would eventually return to your starting point from the opposite direction, having circumnavigated all of reality. The third is an open universe, an infinite, saddle-shaped geometry where space curves away from itself in every direction, leading to a reality of eternal expansion and divergence. For decades, this was a question of pure theory, but we now have a way to measure the shape of the cosmos itself. The key lies in the oldest light we can see, the cosmic microwave background. By meticulously mapping the tiny temperature variations in this afterglow, satellites like Planck have taken the universe's curvature. The results are astonishingly precise. The measurements indicate that the geometry of our observable universe is flat, or so nearly flat that we cannot detect any curvature. This profound flatness is not a coincidence. It is a direct prediction of the theory of cosmic inflation. That initial, violent growth spurt stretched the infant universe so dramatically that any original curvature was smoothed away to near perfection, like flattening the wrinkles on a balloon by inflating it to an immense size. Yet the story may have an even stranger twist. A flat universe does not necessarily mean a simple one. Topology introduces the mind-bending possibility that space could be multiply-connected, meaning it wraps around on itself in finite volumes. The most familiar analogy is a video game world, where moving off the top of the screen brings you back to the bottom. In a three-dimensional version of this, if you peered through a powerful enough telescope in one direction, you might see the faint, ancient light from the back of your own head, after it had traveled all the way around the universe. If the cosmos is indeed finite but unbounded, a vast hall of mirrors with no center and no edge, what does that imply about our ability to ever know it completely? Could every star we see be a single image of the same star, seen over and over again along different cosmic pathways? This large-scale geometry, set in the first moments of inflation, defines the ultimate container for all of existence. The universe we observe is remarkably uniform, a fact that presented a deep puzzle for cosmologists. Why does the cosmic microwave background, the oldest light in the universe, have almost exactly the same temperature in all directions, as if every part of the sky had once been in perfect thermal contact? This is the horizon problem, and its solution required a radical new idea. Physicist Alan Guth proposed that the universe underwent a spectacular growth spurt in its first fleeting moments, a period he called cosmic inflation. In this theory, a minuscule, subatomic patch of the primordial universe was propelled into an exponential expansion, doubling in size over and over again, faster than the speed of light. This unimaginably rapid stretching, occurring in less than a billionth of a billionth of a billionth of a second, took a tiny, homogeneous region and inflated it to a size larger than our entire observable cosmos. This explains the profound uniformity we see, because everything we can observe today originated from a single, connected region before inflation began. Guth himself reflected that the inflationary universe model was too good to be wrong, a sentiment that captured its elegant power to solve multiple problems at once. This same explosive stretching also solved the flatness problem, acting like a cosmic iron that smoothed out any initial curvature, leaving behind the geometrically flat universe our satellites now measure. The engine for this incredible expansion is thought to be a hypothetical field, the inflaton field, which possessed a peculiar property, a kind of high-energy false vacuum that generated a powerful repulsive gravity. As this field slowly relaxed to its true, lower energy state, it released a tremendous amount of energy, reheating the universe and filling it with the hot plasma of particles that would eventually form atoms, stars, and galaxies. But inflation did not create a perfectly smooth universe. At the quantum level, tiny fluctuations in the inflaton field were inevitable, and as space expanded at a breathtaking rate, these microscopic ripples were stretched to cosmic proportions. These minute variations in density became the gravitational seeds for all future structure, the blueprint for the first stars, the great galactic walls, and the vast cosmic voids we see mapped across the sky today. The evidence for this ancient growth spurt is written in the cosmic microwave background, where we can still detect the faint imprint of those primordial density variations. How does it reshape our understanding of cosmic history to know that the entire large-scale architecture of the universe was determined by quantum tremors, magnified to an epic scale in a blink of existence? This profound connection between the very small and the very large suggests that the universe we inhabit is just one possible outcome, one bubble in a far vaster and more exotic cosmic foam. This ancient light is the ultimate cosmic fossil, a snapshot of the universe in its infancy. When you tune an old analog television to a channel of static, about 1% of that flickering snow is the remnant glow of creation itself. This is the cosmic microwave background, the oldest light in the universe, released when the cosmos was a mere 380,000 years old. Before this pivotal moment, the universe was a searing, opaque fog of plasma, where light was constantly scattered by free electrons, unable to travel in a straight line. As expansion cooled the universe, electrons combined with nuclei to form the first stable atoms in a process called recombination. Suddenly, space became transparent, and that trapped light was set free, streaming across the cosmos for the first time. That primordial flash has been stretched and cooled by the relentless expansion of space over more than 13 billion years. Its original visible warmth shifted down into the microwave part of the spectrum, bathing the entire universe in a faint, cold glow of just a few degrees above absolute zero. This radiation is not just old, it is a nearly perfect blackbody, a term physicists use for an idealized object that absorbs and emits radiation with a specific spectrum dependent only on its temperature. The cosmic microwave background matches this theoretical perfection with astonishing accuracy, a hallmark of its origin in a hot, dense, and uniform state. Yet it is the tiny imperfections in this glow that hold the deepest secrets. Across the sky, there are minute temperature fluctuations, variations of only a few millionths of a degree. These anisotropies are not random noise, they are a cosmic treasure map. They represent the faint imprints of sound waves traveling through the early plasma, regions of slightly higher and lower density that were the gravitational seeds for everything to come. The discovery of this background in the mid-1960s by Arno Penzias and Robert Wilson was accidental, but it provided the definitive evidence for the Big Bang theory, earning them a Nobel Prize. Since then, a series of increasingly sophisticated satellites have mapped this faint whisper with exquisite precision. The COBE satellite first confirmed the perfect blackbody spectrum and detected the anisotropies. The WMAP mission provided a detailed baby picture of the universe, revealing its age and composition with unprecedented clarity. Finally, the Planck satellite delivered the most precise map ever, a detailed chart of the early universe's density variations that allows us to measure the universe's geometry, content, and even the timing of its first moments with incredible confidence. These ancient photons have been traveling for over 90% of the universe's history, and they still carry encoded messages about the initial conditions of everything. What can this fossilized light, a relic from a time before stars or galaxies even existed, still reveal about the very laws of physics that governed the first split second of creation? This primordial snapshot is the ultimate benchmark, the starting point from which we measure the entire subsequent evolution of the cosmos. This fundamental benchmark, the ancient light of the cosmic microwave background, is now at the heart of a growing crisis in cosmology. We call it the Hubble tension, and it represents a stubborn discrepancy in one of the most important numbers in the universe, the Hubble constant, which measures the current rate of cosmic expansion. The problem is this: when we use the pristine snapshot of the early universe, the cosmic microwave background, to calculate this rate, we get one very precise value. But when we measure the expansion directly using nearby cosmic landmarks, like Cepheid variable stars and Type 1, a supernova in our galactic neighborhood, we get a consistently faster rate. The universe today seems to be expanding more quickly than our best model of the early universe predicts it should be. This is not a small statistical fluke. The gap between these two methods has persisted and even grown as our measurements have become more and more precise. Cosmologist Wendy Friedman has noted that this tension is either the most exciting thing to happen in cosmology in 30 years or the most unsettling, because it suggests we might be missing something fundamental. If this discrepancy is real and not due to some hidden error in our measurements, it could be the first crack in our standard model of cosmology, pointing toward new physics we have not yet dreamed of. Perhaps dark energy is not a constant, but an evolving force that has changed its strength over cosmic history. Maybe there exists a new, exotic type of neutrino, or some other unknown relativistic particle that was present in the early universe and altered its evolution in a way we have not accounted for. This local measurement crisis forces us to scrutinize the very tools we use to map the cosmos, the standard candles that allow us to gauge cosmic distances. How do we measure something as vast as the universe's expansion? We rely on objects with known intrinsic brightness, like Cepheid stars, whose predictable pulsations act as cosmic yardsticks. By comparing how bright these objects truly are to how dim they appear from Earth, we can calculate their distance and thus the expansion rate. The fact that these two completely independent methods, one looking at the infant universe and one at the contemporary one, refuse to agree tells us that our understanding of cosmic history is incomplete. What does it mean for our quest for knowledge when the universe itself provides us with contradictory data, forcing us to question the very framework we use to describe reality? These stellar explosions are the universe's most reliable mile markers, born from a delicate cosmic dance with a violent end. A Type 1, a supernova, begins not with a single star, but with a pair locked in a gravitational embrace. One of these stars is a white dwarf, the Earth-sized core of a Sun-like star that has exhausted its nuclear fuel. This stellar cinder is supported not by fusion, but by a quantum mechanical pressure, a force that only exists because of a fundamental rule preventing electrons from occupying the same space. If this white dwarf has a companion star, it can slowly siphon material from its neighbor growing in mass. There is a strict limit to this growth, a critical threshold known as the Chandrasekhar limit. Once the white dwarf reaches about 1.4 times the mass of our Sun, the inward crush of gravity overwhelms that quantum pressure. In a single, violent instant, the entire star is consumed by a runaway thermonuclear fusion reaction. It does not just explode, it is completely incinerated, leaving no remnant behind. The brilliance of this event is what makes it so valuable, because every Type 1, a supernova, is triggered by reaching this identical mass limit. The physics of the detonation is remarkably consistent. They all achieve nearly the same peak intrinsic brightness, shining for a brief period with the power of 5 billion suns. This consistency makes them perfect standard candles. Imagine you are standing on a long, dark road at night and you see two identical streetlights. If one appears much dimmer than the other, you instantly know it is farther away. Astronomers do the same with these supernovae. By measuring how dim a Type 1 supernova appears from Earth, they can calculate with incredible precision the distance to its host galaxy. Finding these cosmic beacons is a race against time. Teams of astronomers use powerful telescopes to scan millions of galaxies night after night, searching for that telltale point of new light. When a candidate is found, a global alert is sounded, and observatories around the world and in space swivel to observe the explosion's rise and fall, meticulously recording its light curve. It was through this painstaking process in the late 1990s that two independent teams made the shocking discovery that would win them the Nobel Prize. They found that distant, ancient supernovae were significantly dimmer than their redshifts predicted. This meant they were farther away than anyone had thought. The only possible explanation was that the expansion of the universe was not slowing down but accelerating, a revelation that pointed directly to the influence of dark energy. How profound is it that our ability to measure the entire cosmos, to uncover its most mysterious force, hinges on the precise self-destruction of a particular type of dead star? These cataclysms are not just tools for measurement, they are also the primary forges for the iron in our blood and the calcium in our bones, scattering these heavy elements across space to one day form new stars, planets, and life. The iron in your blood and the calcium in your bones were not born on Earth. Every single atom that makes up our world and us has an epic origin story written in the fiery hearts of stars and the violent deaths of giants. This cosmic process is nucleosynthesis, the creation of the elements, and it is the reason our universe is anything more than a vast cloud of hydrogen and helium. The first chapter of this story opened in the universe's earliest moments, during a brief window known as Big Bang nucleosynthesis. In the first 3 minutes, as the cosmos cooled from its initial unimaginable heat, protons and neutrons began to fuse. They formed the nuclei of the lightest elements, hydrogen, helium, and a trace amount of lithium. This was the foundational seeding of the universe, and to this day, over 90% of all atoms remain as these two simplest elements. But this process could not continue. The universe was expanding and cooling too rapidly to forge anything heavier. For millions of years, the cosmos was a simple soup of hydrogen and helium, waiting for gravity to pull together the first stars and begin the next, more creative phase. Inside the intense pressure and heat of a star's core, a second chapter unfolds: stellar nucleosynthesis. Here, stars like our Sun spend most of their lives fusing hydrogen into helium, releasing the energy that makes them shine. For more massive stars, this is only the beginning. As they age and their cores contract and grow hotter, they begin to fuse helium into carbon, and then carbon into heavier elements like oxygen, neon, and silicon, building their way up the periodic table in a series of nested shells like the layers of an onion. This fusion process is a delicate balancing act, releasing energy and creating new elements right up to iron. Iron is a cosmic dead end. Fusing iron atoms does not release energy, it consumes it. At this point, the star's internal engine sputters and fails. Without the outward pressure from fusion, the core collapses catastrophically, leading to a supernova explosion of unimaginable power. It is in these final, violent moments that the third chapter is written. The incredible energy of the supernova blast and the even more extreme conditions found when two neutron stars collide provide the intense neutron flux necessary to build elements heavier than iron. Through processes with names like the rapid process, atomic nuclei are bombarded with neutrons, building up gold, silver, platinum, and uranium in a single, spectacular burst. These newly forged elements are then scattered across interstellar space, enriching clouds of gas and dust that will one day collapse to form new stars, planets, and life. As the astronomer Carl Sagan so beautifully put it, we are made of star stuff. Every atom in your body, with the exception of the hydrogen, was forged in the heart of a long-dead star and scattered across the galaxy by its explosive death. The carbon in your cells, the oxygen you breathe, the gold in a piece of jewelry, all have a cosmic pedigree billions of years old. When you look up at the night sky, you are not just looking at distant points of light, you are looking at the very factories that built the world you stand on. This profound connection to the cosmos leads us directly to the densest, most extreme objects left behind by such stellar cataclysms. The factories that forge the elements leave behind the universe's most extreme matter. When a massive star explodes in a supernova, its core does not always collapse into a black hole. If the remaining mass is just below that ultimate threshold, gravity performs a different kind of alchemy, crushing the core into a neutron star. Imagine compressing more than the mass of our entire sun into a perfect sphere no wider than a city. The density is beyond human comprehension. A single teaspoon of this material would weigh billions of tons, the mass of a mountain held in your hand. In this state, atoms cease to exist. Electrons are slammed into protons, merging to form a solid, city-sized ball of neutrons, a substance with the density of an atomic nucleus. It is a state of matter that simply cannot exist anywhere else in the universe. Some of these neutron stars reveal themselves in the most precise way imaginable. If a neutron star is spinning rapidly and possesses a powerful magnetic field, it can become a pulsar. Intense beams of radiation shoot out from its magnetic poles, and as the star rotates, these beams sweep through space like the brilliant rays of a cosmic lighthouse. From our distant vantage point, we see a regular, repeating pulse of energy with every rotation, a blink that can be as predictable as the most accurate clock on Earth. Their discovery in 1967 was a moment of pure astonishment. A young graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope she had helped build when she noticed a curious, repeating signal, a pulse so regular it seemed almost artificial. She and her advisor initially humorously labeled the signal LGM for Little Green Men, considering the possibility of an extraterrestrial beacon. They soon realized they had found something entirely natural, yet no less incredible, the first observed pulsar. This incredible regularity makes pulsars unparalleled tools for testing the fabric of spacetime itself. The most famous example is the Hulse-Taylor binary pulsar, a system where two pulsars orbit one another. By meticulously timing their pulses over decades, astronomers confirmed a key prediction of Einstein's general relativity, that the system would lose energy by emitting gravitational waves, causing the stars to spiral slowly inward. This indirect proof of gravitational waves earned Russell Hulse and Joseph Taylor the Nobel Prize and provided the first solid evidence for a phenomenon we can now detect directly. These cosmic lighthouses are natural laboratories for physics under conditions we could never replicate. What happens to matter when it is squeezed to densities where protons and neutrons dissolve into a soup of quarks? How do magnetic fields trillions of times stronger than Earth's influence the very vacuum of space around them? The answers are locked within these spinning city-sized orbs. And when two of them finally spiral together and merge in a cataclysm that shakes the very cosmos, they do not just create gravitational ripples, they forge the universe's heaviest elements like gold and platinum, scattering them across the galaxy to one day become part of new worlds. The universe's most extreme events do not announce themselves with a flash of light, but with a silent tremor in the fabric of reality itself. These are gravitational waves, ripples in space-time predicted by Albert Einstein a full century before we possessed the technology to find them. Just as a boat creates waves in water, Any massive object that accelerates creates distortions in the four-dimensional fabric of the cosmos. But to produce a wave strong enough for us to detect across interstellar distances requires the most violent events imaginable, the final in-spiral and collision of black holes or the furious merger of neutron stars. These waves travel outward at the speed of light, not through space, but as a stretching and squeezing of space itself. For decades, this was considered an untestable prediction, a beautiful but elusive part of Einstein's theory. That all changed on September 14, 2015. The twin observatories of the Laser Interferometer Gravitational Wave Observatory, or LIGO, recorded a signal that would make history. For a fifth of a second, the detectors measured a distinctive chirp, the frequency and amplitude rapidly increasing as two black holes, each about 30 times the mass of our Sun, circled each other hundreds of times per second before finally merging into one. The event released more power in gravitational waves than all the starlight in the observable universe at that moment. This was not seeing the cosmos, it was listening to it, opening an entirely new window onto the universe. This new sense provides information that light simply cannot. Light can be blocked or absorbed by cosmic dust, but gravitational waves pass through matter almost completely unimpeded, bringing us a clear, undistorted signal from the heart of the darkness. They allow us to probe the moments immediately following the Big Bang, a time when the universe was too dense and hot for light to travel freely, but when the fabric of spacetime itself was ringing with primordial waves. Picture the universe subtly stretching and squeezing everything in its path as a gravitational wave passes through. The effect is infinitesimally small, distorting the entire Earth by less than the width of an atomic nucleus, which is why detecting them represents one of the most precise measurement experiments ever conducted. What does it mean for our understanding of reality that we are no longer passive observers of a silent sky, but can now feel the very cosmos vibrate with the echoes of its most cataclysmic births and deaths? This foundational assumption that the universe is largely uniform is the bedrock upon which modern cosmology is built. We call this the Cosmological Principle, the elegant idea that on the very largest scales, the cosmos is both homogeneous and isotropic. Homogeneous means the universe is essentially the same everywhere you might go, with matter distributed evenly when you zoom out far enough. Isotropic means it looks the same in every direction you might look, with no single preferred center or special axis. The evidence for this principle is deeply compelling. It is written in the cosmic microwave background, that ancient light which shows only minuscule temperature variations from one patch of sky to another, a testament to an early universe of stunning smoothness. Further support comes from massive galaxy surveys that map the positions of millions of galaxies, revealing a cosmic web that, when viewed from a sufficient distance, appears statistically similar no matter where you point your telescope. This principle is not just a philosophical preference, it is a practical necessity. It allows cosmologists to apply the same physical laws everywhere and to construct models, like the Big Bang, that describe the evolution of the entire observable universe from a single, knowable set of initial conditions. Our entire standard model of cosmology rests upon this assumption of large-scale regularity. Yet, the cosmos has a way of challenging our neatest assumptions. Astronomers have begun to discover structures of such immense size that they seem to strain the very definition of large scale. One of the most famous is the Hercules Corona Borealis Great Wall, a colossal filament of galaxies stretching over 10 billion light-years across. This is not merely a big cluster. It is a gargantuan ribbon of structure that appears to be one of the largest known coherent formations in the entire observable universe. Its sheer scale raises a profound question: at what point does large scale truly begin? If structures this vast exist, does the universe ever actually become smooth and uniform? Or are we simply not seeing the full picture? Other potential anomalies, like mysterious cold spots in the cosmic microwave background or hints of a preferred direction in the expansion of space, further poke at the edges of this foundational principle. If the cosmological principle is not perfectly true, the implications would be revolutionary. Our models for the universe's origin, its composition, and its ultimate fate would require a fundamental rewrite. It would suggest that our cosmic address is not as typical as we had assumed, that we might be living in a special region of a much more complex and textured cosmos. What if the universe is not a uniform tapestry, but a quilt of regions with slightly different properties, and we just happen to live in one that allows us to exist? This question of our place, of whether we occupy a typical or a privileged vantage point, leads directly to one of the most influential and humbling ideas in all of science. Our very existence seems to whisper a secret about the cosmos. The fundamental laws and constants that govern reality appear to be balanced on a razor's edge, a delicate arrangement that makes our universe strangely hospitable to life. This is the heart of the Anthropic Principle, a concept that forces us to confront why the cosmos is the way it is. Physicist Brandon Carter, who introduced the term, framed it in two parts. The weak Anthropic Principle is a simple statement of selection bias. We observe a universe compatible with our existence because we could not possibly observe one that is not. It is a logical truism, but one with profound implications. The strong versions of the principle, however, venture further, suggesting that the universe must, in some sense, have parameters that allow observers to emerge. The evidence for this apparent fine-tuning is startling. Consider the nuclear forces that operate inside stars. The strong nuclear force which binds atomic nuclei has a very specific strength. If it were just a few percent stronger, protons would pair up so readily that all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for stars like our Sun. If it were slightly weaker, complex nuclei like carbon and oxygen could never form at all. The very carbon that is the backbone of our biology exists because of a fortunate resonance in the nuclear processes within stars, a lucky match that allows for its abundant production. The cosmological constant, the energy density of empty space, is another example. If this value were much larger, the universe would have blown itself apart before galaxies could ever form. If it were slightly more negative, the cosmos would have collapsed back on itself long ago. We find ourselves in a universe that permits galaxies, stars, planets, and life, not because of a chain of endless coincidences, but perhaps because only such a universe could give rise to creatures who ask such questions. Does this mean the universe was somehow designed for life? Not necessarily. One compelling explanation lies in the possibility of a multiverse. If our cosmos is just one bubble in an infinite, bubbling foam of universes, each with its own random set of physical constants, then it is no surprise that we find ourselves in one of the rare, life-friendly ones. In the vast majority of universes, the constants would be wrong, and no one would be there to notice. This perspective transforms the question from why is our universe so special to how could we be anywhere else. The Anthropic Principle stands at the crossroads of physics and philosophy, challenging us to ponder whether the laws of nature are a unique, inevitable recipe, or just one random draw from a cosmic lottery of unimaginable proportions. This profound fine-tuning of our universe's laws may not be a miracle, but a simple matter of statistics. If our cosmos is just one bubble in an infinite cosmic foam, then a life-friendly universe is not an unlikely accident, but an inevitable outcome somewhere. This is the Multiverse Hypothesis, a radical extension of our cosmological theories that suggests our entire reality is but one page in an endless library of universes. The simplest version is the Level 1 multiverse, born from the theory of eternal inflation. This idea posits that the rapid expansion of space, which shaped our early universe, never truly stopped everywhere. Instead, it continues eternally in a background meta-universe, occasionally stopping in pockets to form isolated bubble universes like our own. These other cosmic domains would exist far beyond our observable horizon, forever out of reach due to the finite speed of light, but they would all share the same fundamental physical laws as ours. A more exotic concept is the Level 2 multiverse, emerging from string theory's landscape of possibilities. Here, the extra dimensions proposed by string theory can curl up in a vast number of different ways, perhaps 10 to the 500 or more distinct configurations. Each of these vacuum states corresponds to a different universe with its own unique set of physical constants, a different strength for gravity, a different mass for the electron. In this staggering plurality of realities, some universes might be stillborn, collapsing instantly. Others might be vast, empty voids. Our universe, with its specific, life-permitting constants, would be just one possibility among an inconceivable multitude. Then there is the quantum many-worlds interpretation, which proposes a different kind of splitting. In this view, every time a quantum event occurs with multiple possible outcomes, the entire universe branches to accommodate each and every possibility. In one branch, a radioactive atom decays; in another, it does not. This process would happen constantly, generating an ever-expanding tree of parallel realities where every conceivable history plays out. The multiverse offers a powerful, if controversial, answer to the puzzle of fine-tuning. There is no need for a designer if every possible set of physical laws exists somewhere. We simply reside in one of the rare bubbles where the numbers allowed stars, planets, and eventually observers to arise. This idea, however, pushes at the very boundaries of science. If these other universes are permanently causally disconnected from our own, if no signal or observation can ever reach us from them, can the multiverse hypothesis ever be tested or falsified? Is it a scientific theory or a philosophical proposition? The challenge is to find some indirect imprint, some subtle signature in the cosmic microwave background or the distribution of galaxies that might hint at a collision with another bubble universe in the distant past. Without such evidence, we are left with a profound philosophical choice. Do we accept the bizarre multiplicity of realities as the most natural explanation for our own existence? Or do we cling to the hope that a single, unique theory will ultimately explain why our universe is the way it is? This question of multiple realities forces us to re-examine the most familiar dimension of all, the steady, one-way flow of time that structures our entire lives. Our daily experience of time's steady march may be the universe's most convincing illusion. We feel it slipping from future to past, an irreversible flow that structures every moment of our lives. Yet the fundamental laws of physics, from Newton's mechanics to Einstein's relativity and quantum theory, show a startling symmetry. They work just as well whether time runs forward or backward. So why does our reality feel so decisively one way? The answer may lie in a concept called entropy, which is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This gives us the thermodynamic arrow of time. Think of a drop of ink diffusing in a glass of water. It spreads out into a uniform cloud, moving from a state of low entropy order to high entropy disorder. You would never see the scattered ink particles spontaneously gather back into a single, neat drop. This relentless increase in disorder, from the cooling of your coffee to the burning out of stars, gives time its apparent direction. But entropy is not the only arrow. There is also the cosmological arrow, defined by the expansion of the universe. As space stretches, it creates the conditions for increasing entropy, scattering energy and matter into a more disordered state. And then there is the psychological arrow, our own internal perception of moving from past to future, which may be a direct consequence of our brains processing information in a universe where entropy is rising. Our memories are records of past events, and those records are only possible because the past was more ordered than the present. This trio of arrows all point in the same direction, creating the consistent flow we experience. Yet, Einstein's theory of special and general relativity paints a radically different picture, one often called the block universe. In this view, the distinction between past, present, and future is a stubbornly persistent illusion. Space-time is a static, four-dimensional manifold where every event, from the birth of the universe to its potential end, already exists. Your birth, your life, and all that is to come are fixed coordinates in this vast, unchanging structure. There is no universal now, no privileged present moment sweeping through reality. What you perceive as the flow of time is simply your consciousness moving along your personal world line within this eternal block. Physicist Carlo Rovelli takes this a step further, suggesting that at the most fundamental level of reality, time might not exist at all. In his work on loop quantum gravity, he proposes that time is not a primary ingredient of the universe but an emergent property, a macroscopic approximation that arises from our limited thermodynamic perspective, much like the concept of temperature emerges from the jostling of countless molecules. If time is not fundamental, then what are we truly experiencing? How do we reconcile the visceral urgency of a passing moment with the possibility that the past and future are just as real as the present? This questioning of time's fundamental nature forces us to look at reality itself as a pattern of information, a code that might be written into the very fabric of the cosmos. This radical rethinking of reality suggests that the universe might be a cosmic projection, a hologram of information. The holographic principle proposes that all the information describing everything within a three-dimensional volume of space, every star, every planet, and every one of us, could be entirely encoded on its two-dimensional boundary, like a fantastically complex DVD surface storing a seemingly three-dimensional movie. This astonishing idea did not emerge from pure speculation, but from the paradoxical thermodynamics of black holes. Physicists exploring black hole entropy realized that the maximum amount of information or disorder a region of space can contain is not proportional to its volume, as common sense would suggest, but to the area of its surface. A black hole's entropy is precisely calculated by the area of its event horizon in Planck units. This implies that all the information about what fell into the black hole is not lost inside the singularity, but is somehow smeared and stored on the event horizon's surface. This insight, pioneered by scientists like Gerard T. Hooft and Leonard Susskind, was then extended to the cosmos at large. It challenges our most basic intuition about the world. We perceive a three-dimensional reality, full of depth and volume, yet the holographic principle suggests this is an emergent illusion. The true, fundamental degrees of freedom, the complete description of our universe, might exist on a distant, two-dimensional surface that we can never see or access. Our lived experience of moving through a voluminous space would then be a kind of decoding of that information, a projection into a higher dimensional appearance. If this is true, then the universe is not made of tiny, point-like particles, but of indivisible bits of information or pixels woven into the fabric of spacetime at the Planck scale. The resolution of our reality would be finite, and the smooth, continuous space we perceive would be a very good approximation, much like a digital photograph appears smooth until you zoom in to see the individual pixels. This leads to a profound and unsettling question. If we are living within a holographic projection, what is the nature of the deeper reality that encodes our existence? Are we the output of some vast cosmic computation? As we push our understanding to these absolute limits, we must also confront the boundaries of knowledge itself, a frontier defined by the very nature of light and information. Even as our understanding deepens, we must face a humbling cosmic truth. There are fundamental boundaries to what we can ever know, walls in space built not by our technology, but by the very laws of physics. The universe is expanding, and this expansion places absolute limits on our cosmic vision. The first of these is the particle horizon. This is the ultimate edge of our observable universe, the maximum distance from which light has had time to travel to us since the Big Bang. Everything we can possibly see, from the nearest star to the most distant galaxy, lies within this vast but finite sphere. Yet there exists a second, more final boundary, the cosmological event horizon. This is not the edge of a black hole, but a similar concept applied to the entire cosmos. It marks the point beyond which galaxies are receding from us so quickly, due to the acceleration of dark energy, that their light can no longer ever reach us. Any event occurring in those galaxies now is forever separated from our future. They have passed beyond our causal reach, their stories lost to us for all time. This leads to a startling reality. Many galaxies we see today at the very limits of our view are already crossing this threshold. Their light reaching us now is the last message they will ever send. In the far future, as the expansion continues to accelerate, our observable universe will shrink to a much smaller collection of nearby galaxies, all else fading to black. Future cosmologists looking up at a dark, empty sky would have no evidence of the cosmic microwave background, no expanding universe, and no clue that there was ever a vibrant cosmos of billions of galaxies. They would see only a static, island universe, and their science would draw profoundly different conclusions. This inherent limit forces a profound philosophical weight upon us. We live in a privileged sliver of cosmic time, a window where the evidence for the grandest story is still visible. Our quest for knowledge is not just a race against our own ignorance, but against the relentless expansion of space itself. What does it mean for our search for meaning that the cosmos itself conceals vast portions of its own history behind unbreachable walls? This contemplation of our unique window of awareness brings us to the final and perhaps most personal cosmic mystery. Our profound isolation in the cosmos may be the universe's most unsettling message. With trillions of planets orbiting countless stars, the galaxy should be teeming with life, a vibrant cosmic community. Yet when we listen, we are met with an immense and puzzling silence. This is the Fermi Paradox, a contradiction that challenges our very place in the cosmos. Physicist Enrico Fermi famously captured its essence during a casual conversation in the summer of 1950, asking a simple, devastating question: but where is everybody? The universe is ancient, nearly 14 billion years old, providing ample time for intelligent civilizations to arise, develop technology, and spread across the galaxy. Given the sheer number of potentially habitable worlds, the silence is deafening. One of the most sobering resolutions is the Great Filter Hypothesis. This idea suggests that the evolution of life from simple beginnings to a spacefaring civilization requires passing through a series of critical steps, and at least one of these steps is extraordinarily difficult, if not impossible, for most life to achieve. This filter could lie in our past, a barrier we were fortunate to cross. Perhaps the genesis of life itself from non-living chemistry is a cosmic fluke, or maybe the leap to complex, multicellular organisms is the true bottleneck. The more unsettling possibility is that the great filter awaits us in our future. It could be that all advanced civilizations inevitably discover a technology that leads to their own destruction, or they encounter a natural cosmic phenomenon that sterilizes worlds. The silence, then, would be a grave warning. Other explanations are less dire but equally mind-bending. Perhaps intelligent life is common, but it is simply too alien for us to recognize. Their methods of communication, their very perception of reality, might be so different from our own that their signals are indistinguishable from background cosmic noise. Or they may have chosen to remain hidden, observing the universe quietly for reasons we cannot fathom. Another possibility is one of cosmic timing. The universe is vast in both space and time. Other civilizations may have risen and fallen billions of years before our sun even ignited, or they may be destined to emerge long after our own star has died. We could be a lonely, early voice in a cosmos that is only just waking up, or a latecomer to a silent, empty party. Our understanding of space and time is central to this puzzle. The vast distances between stars create an ocean that is incredibly difficult to cross, potentially isolating civilizations forever. And the finite lifespan of stars and the accelerating expansion of the universe impose a strict deadline on any galactic conversation. Does the great silence tell us that intelligent life is a fleeting, rare spark in the cosmos? Or does it reveal the ultimate fate of all technological societies, a quiet fade into obscurity? This final mystery brings our journey to a close, not with definitive answers, but with a deeper, more resonant wonder. The cosmos is filled with phenomena that rewrite our understanding of reality, leaving us with more questions than we started with, and a profound appreciation for the mystery that surrounds us. These 25 cosmic threads are not separate strands, but a single, interwoven tapestry. Dark energy provides the relentless outward push that stretches the cosmic stage, while dark matter acts as the invisible scaffolding, sculpting the galaxies that form upon it. The quantum fuzz of the vacuum, seething with virtual particles, was stretched by inflation into the gravitational seeds for all cosmic structure, linking the behavior of the smallest things to the grandest architectures of the universe. This grand synthesis reveals that our universe is a story told by its own constraints and contradictions. The fiery war between gravity and dark energy dictates the ultimate fate of the cosmos, a battle whose outcome is written into the geometry of space itself, measured by the fading light of supernovae. The profound enigmas of black holes and Hawking radiation force a confrontation between the smooth spacetime of general relativity and the grainy uncertainty of quantum mechanics, a clash that points toward a deeper theory of quantum gravity. Our very perception of time's flow emerges from the increase of entropy, which is itself tied to the universe's expansion, suggesting that our most fundamental experience of reality may be a beautiful macroscopic illusion. Each new discovery, from gravitational waves to the holographic principle, does not simply add another piece to the puzzle. Instead, it forces us to reassemble the entire picture we thought we had, redefining the very questions we ask. The quest to understand the cosmos is not a linear accumulation of facts, but a continuous, humbling process of rewriting the story of everything, including our own place within it. How does this interconnected web of mysteries change not just what we know, but how we feel about our own fleeting, conscious moment within this vast, unfolding narrative? This evolving quest reveals a universe far grander and more mysterious than we once dared to believe. Our journey through these cosmic wonders shows that every answer unravels into a deeper, more beautiful question. The invisible hand of dark matter sculpting galaxies, the silent pressure of dark energy pulling the cosmos apart, the profound riddles of black holes and the possibility of parallel universes, these are not distant abstractions. They are the very fabric of our reality, challenging us to reconsider what it means to exist within this vast, unfolding story. They push at the boundaries of our comprehension, forcing us to confront the nature of our own consciousness and our fleeting, yet precious, place in the cosmic order. As Carl Sagan so eloquently reminded us, somewhere, something incredible is waiting to be known. This is an invitation to carry that sense of wonder with you. We would love to hear which of these phenomena reshaped your perspective the most. So share your thoughts in the comments below. If you enjoyed this journey to the edge of understanding, subscribe for more, and never stop looking up at the stars and wondering what else is out there.